Hi everyone, my name is Neha Kardam and in this lecture we're going to learn about flip-flops. So let's get started. So these are the topics which we'll be covering in this lecture. We will learn about combinational versus sequential logic circuits, RS flip-flop, clocked RS flip-flop, D flip-flop, JK flip-flop, latches, which are simple memory devices, and then applications of latched encoder and decoder, then triggering of flip-flops, and then Schmitt triggered device. So let's start with the logic circuits. So logic circuits, they are classified into two groups. The first group is the combination logic circuits and the other one is the sequential logic. Combination logic circuits we have already seen in our previous lecture. So these are the basic building blocks of the combination logic circuits, your inverters, AND gates and OR gates. And with the use of these three gates, we can make other gates like NAND gates, NOR gates, and XOR gate and XNOR gate. And then we have another type of circuits which are called sequential logic circuits. And in this sequential logic circuits, the present output basically depends on the present input as well as on the past outputs. So the base for the flip-flop and counters and resistor is the sequential logic circuits. And you can see here, this is the block diagram of a sequential logic circuit where you have a combination logic circuit here, and then you have a memory element here. So in this memory, the past output will be stored, the output which is coming from here, and that will be called your past output, and that will be sent through the this feedback stored in the memory element and then feedback to the input here. And when they come here, then they will be called your past inputs. Okay, now here the memory, you see, it is nothing but the flip-flop. So before the flip-flop, when they were invented, there were other methods were there to store the bits. For example, is your cascade NOT gate arrangement. So which you see here, this is the cascade NOT gate, and you see how from 0 to 1 and 1 to 0 using the two NOT gates we got the same output here, which we sent it here, and then that output is basically stored and sent back to the input. So this kind of arrangement is used in a memory previously when flip-flop were not invented. And there's one more thing I want to tell you is the counter. Like in a counter, let's say if you want to count from 0 to 9 and you want to make a counter for that, so how you are going to make it? So you will just add 1 to it, like 0, starting from 0, and then you will plus 1, that will make up your 1, and that 1 is basically your output, and that will be sent to the next next stage, and this previous output is sent here, and then you just add 1 every time. So you see, you add 1 here, then you have 2, and this is again acting as your previous output fed back here, and then adding just 1 to this, that will make up your 3, and then from 3 plus 1, that will make up your 4. So this output is fed back here. So you see that how we are storing the output and then sending back to the next state, the same here, and so on. It will happen till 9. Okay, so to store the output, for that we need a memory, and that memory is basically your flip-flop. Okay, now let's see some quiz questions. The first one says the basic building block for our combinational or sequential logic circuits include logic gates such as NOT, AND, and OR. So it is going to be the combinational, because in a combinational we have the basic logic gates which are NOT, AND, and OR. So combinational. And then basic building block for sequential logic circuit include various flip-flops. So is it a true statement or false? So it is the true statement, because that's what we learned in the previous slide. The basic building block for sequential logic circuit contains the flip-flops, or which is also called your memory. So this statement is true. And then a flip-flop is an example of a device used in combinational or sequential logic circuit. So definitely it's going to be the sequential. So we have sequential here. Now let's begin with first flip-flop, which is called your RS flip-flop. And this is the symbol of RS flip-flop. You see RS flip-flop is made up of two NAND gates. These are the two NAND gates which are used, and if you put them together in this way, then that will make up your RS flip-flop. And here you see the symbol of RS flip-flop. We have a set and reset here, and then normal output, and then a complementary output. Okay, so now let's see the truth table to understand what is happening here. So if you provide 0 0 to your set and reset, okay, so what will happen at that time? Your output, your Q will be 1 and your complementary will be 1. So imagine if your Q is 1, then in a complementary state it should be 0, but that doesn't happen. So this is so this first stage which you see is 0 0, when S and R are 0 0, then there is no change in the output, and they both are same. So this state is not actually true, because the other Q bar should be complementary of Q. So that's why we do not use this state. Okay, in SR flip-flop, this is the, you can say, drawback, that we do not use this stage, and that's why it says here that it is a prohibited state, and this state is not used. So this is the case 1, and a second case is a set state, when you put 0 here, when you give 0 here and 1 here, which means if you give 0 here and 1 here, and if you follow the process like the way how input goes into the NAND gates, and you have to assume that there is some output already there, so maybe say 1 or 0 is here, and based on that, if you evaluate and if you give 0 here and 1 here, you will always get Q is equals to 1 here and Q dash is equals to 0. Okay, so when you give set, when your set is 0 and reset is 1, then at that time your Q is going to be 1. Okay, and then we have next state, which is called your reset state, and in reset state, when you give S is equals to 1 and R is equals to 0, in that state your Q is going to be 0 and Q dash is going to be opposite, which is 1. Okay, so you see that what is happening here, when you press the set, or you provide here 0 and 1, then your output is basically setting. Okay, and when you press reset, when you provide these inputs, then your output is reset. So you see, when you have set input, then your output is 1, which means set, and when you reset or you provide reset input, then your output is reset to 0. Okay, and then there is a last state, which is 1 1. When you provide, when your S and R, they both are 1, then what will happen in that state, whatever you had previously in your Q and Q bar, that is going to remain the same. Okay, whatever input you have provided, for example, if you have provided reset before this whole state, and your output is 0 1, and then you press 1 1 to SR, then your output is going to be 0 and 1, the same. So it will hold the state when you provide S and R as 1 and 1, then there is no change in the output, and your output is basically called your memory state. It will save the bits into the memory. Okay, so this whole operation RS flip-flop is basically for active low inputs. Okay, always remember this is for active low, which means if you, again going back to these two states, S set and reset, which means when you provide 0, when you provide 0 to S, and 1 to R and 1 to R, in that state your output is 1. Okay, and that is why we say active low inputs. So when you have provided low input, then your output is activated. Okay, so this is your active low, or when you provided low input, then your output is activated. and then in the second case when you provided 1, then your output is low, and that is the function of reset. You reset the value to the 0. So this truth table is based on active low inputs, and you can make the RS flip-flop using the NOR gates also. Okay, but there will be some changes in the truth table, and in place of this NAND gate, if you replace them with the NOR gate, okay, if you replace them with the NOR gate, then that will be your another type of latch or another type of flip-flop. Now let's quickly see here the NOR SR flip-flop. So you see, this is the logic diagram for NOR SR flip-flop. In place of NAND gate, we have used NOR gates, and then this is S and this is R, and then Q and Q dash are our output. And then here you see is the truth table for NOR SR flip-flop. So S and R, and then Q and Q dash your output. Now here you can compare, like it is different than your NAND flip-flop. When you have 0 0, then in that case there will be no change, so this NC stand for no change in Q and Q dash. So latch remained in the present state, which means this is the memory state, or you can say this is the hold state, whereas in the NAND gate we have the hold state when S and R are 1. And then in the second state, when S is 1 and R is 0, in that case your Q, output Q is 1 and Q bar is 0. And then when your S is 0 and reset is 1, then your Q is 0 and Q dash is 1. And when they both are 1, at that time your output is 0 0, which is an invalid condition, or you can say this is the prohibited state. Okay, so if you notice that this type of flip-flop is basically your active high. Why? Because when you press S is equals to 1, in that case your output goes high. So when your S is 1, when your set is 1, then output is also set, which is equals to 1. And when your reset is 1, then in that case your output is 0. And that's what we want. Okay, when we want, when it is set, then Q should be 1, and when it is reset, then Q should be 0. But the only difference is here it is an active high input. When you are providing the active high input here, then your output is turning high, whereas in this case this is the active low input. So when you were providing 0 to set, then your Q was turning high. So you can see here when your when your set is 0, then Q was high, and in the second case when your R is 0, then your Q is turning 0. So this is active low and this is active high inputs, and these are the two different types of flip-flops under RS. Now let's see some quiz questions. What is the mode of operation of the RS flip-flop? Set, reset or hold? What is the output at Q from the RS flip-flop at active low input? So there will be some different conditions, and we are going to see like what would be the answer for that. So when your set is 0 and your reset is high, then what happens? Since it is an active low input, then what will happen? When your set is 0, then output is, which is Q, is going to turn high. Okay, and Q dash will be the complementary of Q, so this is going to be 0. So answer is this is the set mode of operation, and the output will be high. Now second is when they both are high. So when they both are high, then that state is basically your memory state, which is your hold state, and both our output will be this Q will be high and then Q dash will be 0, or whatever the previous state you had, that will appear here. Okay, so when they both are high, when they both are 1 1, at that time the mode of operation is going to be your hold or the memory state. And then we have the third case when the set is 1 or set is high and R is low or R is 0. When R is 0, then Q is going to reset. So this is the reset state, and then Q is going to be low. So that's how you got here. Now next we are going to see the clocked RS flip-flop. So In the sequential circuit, a lot of processes takes place, which goes from one to another, and thus there should be a control over the process. And so for that we use the clock. So now we are going to see how we can use the clock. So in this RS flip-flop, we have a clock here. This portion you already know, this is your RS flip-flop, and before that what we have here is the clock. Okay, so the clock signal is provided, and this clock basically decide the time of the input, and we can also decide the speed of the circuit by changing the clock frequency. And this, let's see the truth table with the clock. So this is the truth table for clocked RS flip-flop, and you can notice that we have a clock here, and a pulse is given for three different stages when it is in hold, reset, and set. So here you note that we have active high inputs, right? If you notice this block diagram here, we do not have a complement. We directly we are giving the set and reset, so that this is our active high inputs. So now if you use this circuit, and if your clock is 1, if your clock is 1, which means your 1 is going in here and you have some input here. So let's say if your S is 0 and R is 0 and your clock is 1. So if you do the process like how what will reflect on your output of these two NAND gates, and further at output of Q and Q bar, then you will see that there will be no change. Okay, in that case when you have a positive pulse going. And then in the second case, when it is a reset, which means you are giving 1 to R and S to 0. So again, just keep in mind this is the active high inputs. That's why we are giving R is equals to 1 and S is equals to 0. Whereas in the previous RS flip-flop, when we didn't have the clock, at that time we were, and at that time it was active low input. So you can go back to the previous slide, and then you can look it up. Like in that one we had here complement, and we were giving active low inputs, whereas here we are giving active high inputs. And if R is 1, then your Q is going to be 0 and Q bar is going to be 1, because when this is high, this is resetting the output. And in the third case, when set, which is the set mode of operation, and in that mode your S is equals to going to be 1 and R is equals to going to be 0, and clock is again is 1. So when clock 1 pulse is given, then at that time your Q will be set, which means Q will become 1. So that's what you see here. When S is 1 and R is 0 and clock pulse is provided, then Q will become 1, and Q bar is basically the complement of Q, so that's why you got 0 here. And then in this case, when you have a clock and you have active high inputs, then you will have a not used stage, or a prohibited stage, which is at input 1 1, when your S and R are both 1. Then your output will not your output will be this, which is basically not true. It cannot be possible, because if Q is 1, then Q bar should always be 0. So that's why this stage is not used when your S and R both are 1. Okay, so this is a clocked RS flip-flop. Now let's look at some quiz problems. So what is the mode of operation of the clocked RS flip-flop? Set, reset, hold. What is the output at Q from the clocked RS flip-flop? Active high inputs. So let's see. So in this case we have high is equals to S is high and R is low, and clock pulse, positive clock pulse, you can see, is provided. Then in that case this is a set operation. Set operation means if S is equals to 1, then Q is going to be 1 when the clock is positive, or clock is 1. So this is a set mode of operation and Q is high. Second state, when your S is low and R is low and your clock pulse is 1. So this type of mode of operation is your memory state, or you can say that hold operation, in which whatever your output your Q and Q bar had previously, it will be stored there. So this is the hold operation and Q will be high. And then third mode of operation, when set is 0 or set is low and R is high or R is 1 and clock is positive, in that case when your reset is high, then your Q is going to be 0. If Q is 0, then Q bar is going to be high. So this is a reset mode of operation and Q is going to be low. So that's why you have here low. Now next we have the delay flip-flop, or it is called D flip-flop, and this is the symbol for D flip-flop. So here the word D, this stands for delay, and this describes what happens to the data or information at the input D. So data could be 0 or 1 at the input D, which is delayed 1 clock pulse from getting into the Q output. And these D flip-flops, they are sequential logic devices which are widely used in the temporary memory devices, and they are wired together to form shift registers and storage registers. Now let's see the truth table. So in this you can see we have two new things, which is PS. PS is basically your preset, and CLR stands for your clear, and that those two you can see on the symbol also. So we have this PS preset here, and then clock here, and then you notice this bubble. This basically represents your low input, active low input. Okay, and this is for these basically provides your asynchronous input to the flip-flop. So now what is asynchronous input? It is basically the input on a flip-flop which have control over the outputs, which is your Q and Q naught, regardless of the clock input status. So these inputs, these are your called preset and clear, and these input basically drives your flip-flop to set state, while the clear state, you see this CLR input, it drives the output state to the reset state. Okay, so what happened when you provide PS, this preset input sets, it will set the output Q to 1 when your enable logic is 0. So when you provide 0 logic here, as you can see here, when you provide 0 logic here, then it will set the Q. Whereas when you provide 0 logic to the clear, then it will reset the Q. Okay, so you can see that this is active low input. So when you are providing 0, then your Q is going high in case of preset, and in case of clear, and clear is used to clear the output, and when you provide 0 to the clear, then it will clear the output to 0. Okay, so that's your preset and a clear, which is used as a asynchronous input. And then you have a clock here. So when this is 0, then in that case, whatever clock or D input you provide, it doesn't matter. Your Q is going to be 1. Okay, and the same is here with the clear. If you send 0 at the clear, then whatever clock or input you will provide at D, it doesn't matter. Your Q is going to be 0. And next we have a prohibited state. In the prohibited state, when these preset and the clear, they both are 0, then whatever input you provide at the clock and at the D flip-flop, D input, then your output is going to be 1 1, and which is basically not possible. These two cannot have the same value. One has to be complement of other. So this is a prohibited state, that's why, and this state is basically ignored and it is not used. And then we have these two states, which are also called your transfer data state. So in the set, and you can see here, this is set and reset basically goes through this D input. So when you provide 1 to this D, okay, when you provide 1 to the D, you can see here 1 to the D is provided, and your clock is positive in this case. Okay, and when you want this to work, you have to set this to 1 1. Okay, preset and clear. So when you have 1, the same data will be transferred to the output. So when your D is 1, then output is going to be 1, and Q bar is going to, or Q naught is going to be your complemented. And in the second case, when your preset and clear are 1, your clock is positive, then you have, if you provide 0, then your output will be reset to 0, and then your Q naught is going to be 1. So if you notice here in the clock input of this IC symbol, you see that this triangle shape here. This basically represents your edge triggered. Okay, so edge triggering is basically given by this clock, and you can say that this flip-flop is edge triggered. Okay, so and it is also written here, when your output, this is the positive clock, which means your output transition, your transition of the clock is going from low to high. Okay, so this was the truth table for D flip-flop. And last two states are important for us because these are the transfer data stages, and whatever you provide at the D, that will be transferred to the Q, and here you provided 0, transferred to the Q output. And these are your asynchronous inputs. Now let's go to the next slide. So we have a couple of questions. What is the mode of the operation of the D flip-flop? What is the output at Q from D flip-flop? So we have a preset set to 0, and D is set to 1, and clock is positive, and your this clear is basically your 1. Now if you notice that your preset and clear, they both are not 1. Your preset is 0 and clock is your clear is 1. Then in that situation, this is your asynchronous input you are giving. This is the asynchronous stage right now going on, and at this stage it does not matter whatever you give here. What matters is these two. Okay, so at asynchronous input you will see at these input, and you will also have to notice these bubble. This bubble basically represent the active low input, which means if you provide 0 or low input to the preset here, then what will happen? Your output is going to turn on, or which means your output will be high. So we can say that the mode of operation is asynchronous, and your, in this case, when your preset is low, then your output is going to be high. And then we have next case, when they both are high, preset and clear is both are high, then this is kind of synchronous mode. And in this you will look at the input which is going into the D and the clock. So clock is your positive and your input is low in at the D, so the same data will be transferred to the Q. So your Q is going to be low and Q naught is going to be high. So your answer is going to be low, and the mode of operation is basically reset. By giving the low, your output is being reset. And then we have a third mode of operation where preset and clear, they both are high, and then your clock is your positive, and then your D is 1, which is high. You are giving high input, so your output is also going to be high, and your mode of operation is set here. The next important flip-flop is the JK flip-flop, where let's see this symbol of the JK flip-flop, where this J and K are both inputs of the flip-flop, and we have a clock also here, and then the preset and the clear. And preset and clear, again, they are active low input going into the flip-flop. So now I hope this portion you all understand right now. When your asynchronous set is 0 and your clear is 1, then whatever input you give to the clock and J and K, what will happen? Your output is going to be turned on, your Q is going to be set, and this is going to be 0. So here we have a active low input. That's why when you have 0 here, your Q is going to be 1. And in the second stage, which is the reset stage, and when you give 0 to the clear and preset is 1, then whatever input you give at the clock and at J and K input, you will get 0 as your Q and 1 as your Q naught, which means your output is being reset. And third is a prohibited stage. When you have both 0, preset and clear, they both are 0, then whatever input you give at these points, clock, J and K, your output is going to be 1 1, which means this stage is not going to be used. So when you have 0 0 at both the input of preset and clear, so that at that point that stage is not going to be used. And then now we have here, so you have a hold stage when your preset and clear, they both are 1. So now for the rest of the stages, just remember that when these two are 1, preset and clear, then your synchronous operation will happen. And right now we have a high to low clock pulse. High to low, it is different than your previous flip-flop. The reason why, because you have a bubble here and then this triangle. So that's why you have high to low. Previously you didn't have this this bubble, and that's why it was low to high, and with the bubble it is high to low transition of the clock is taking place. So every time your clock goes from high to low, your basically input will be triggered, and then your output will be generated based on whatever the input is available at the J and K and at the preset and clear. So when your preset and clear are 1 and your clock is going from high to low and it is being triggered at that point, then if you have J and K as 0 0, then that will be called your no change state or a memory state, okay, or a hold state. So these are 3 different names which you can use for this particular state. And next we have a reset. When you have a reset, which means we are going to reset the Q, and Q will reset to 0. And when we have set, then we will set Q equals to 1. Okay, so let's see here. When we have reset, which means J is equals to 0, and when your K is equals to 1, then in that case your Q is going to reset to 0 and then Q naught is going to be 1. And when you have set, then in that case J should be 1 and K should be 0, and then your output will be 1 for Q and your Q naught is going to be 0. And then you have fourth state. When your preset and clear are 1 1, then you have a fourth state in which the toggle happens. Okay, so if you have J and K as 1 1, then whatever your input or whatever the Q was previously, it will toggle. Okay, if it was 1, then it will go 0. If Q was 1, then it will go 0, and then Q naught will become 1. Okay, or if it was 1, then it will go to 0 and Q naught will become 1. So here is the benefit of this stage. So you remember in the last SR flip-flop, there was one stage which was prohibited or was not used when your inputs were 1 1. At that stage was not used. But here we have the benefit that we are able to use all the 4 cases. You see all these 0 0 1 1 and 0 1 0 1. So all these 4 cases we are able to use in the JK flip-flop, and this is the benefit of this JK flip-flop, that we can utilize all the 4 stages. In the first stage, when you provide JK is equals to 0 0, then that will become your memory stage. And when we use JK as 0 1, then you can basically reset your output. And when you have 1 0, then you can set your output, and when you have 1 1 at the JK, then whatever your output was, it will basically have opposite, or it will toggle. So you see here the benefit of this type of JK flip-flop compared to the SR flip-flop. Now let's move on to the quiz. What is the mode of the operation of the JK flip-flop, and what is the output at Q from the JK flip-flop? So let's see. We have to determine what will be the mode of operation and what will be the output at this particular stage. So when your preset is low and clear is high, so at that time you know that when this is 1 and you have active low input going in here. So right now this is at a asynchronous mode, and in asynchronous mode, this is going to be preset because you have low here. When this low goes here, then Q will become 1 and this will be your preset. And when you have both high, so now this is the synchronous mode, and in this one you have to look for what input you are giving at J and K and at the clock. So clock is your going from high to low in this case because you have a bubble here, and then your J is high and your K is high. When they both are high, then at that time your output is going to be low. So, and this is the stage of toggle. So we are assuming that we have high previously, so now your Q is going to go low. So this is a toggle stage and you have Q is equals to low. So you can assume like if we had like Q high, and then after this stage, if we have this stage, then from high to low it will go your Q. And then let's see after this what will happen. We have preset and clear, both are high, so again synchronous mode, and then we will look for J and K. So J is low and K is high, and then you have high to low input clock going in. So this type of mode of operation, in this case your output will again is going to remain low, and if it is low then this will be your reset state. Okay, so you have reset state here. And now let's see next. When your preset and clear, they both are high and J is high and the K is high, then what will happen? So this is a toggle state actually. When you both are high, then this is a toggle state. Then what will happen? So if you consider from the previous state, so previously you had low, and if you have toggle again, then this low is going to go high. So that's why you have high here. And then let's see next, when you have preset high and clear high and J and K, they both are high, and your clock is going from high to low. So again, this is a toggle state, but then what will happen to the Q? So your Q will go low in this case. And then you have this state when you have preset is high and clear is low, and then whatever, if these two are different, then whatever you give here, it will not matter. Okay, the matter is what matters is what you are giving to the preset and clear. Now it is at a asynchronous input mode, so we will look for what we have at preset. We have high and clear is low, so, and this is the active low input. So if you provide 0 here, then Q is going to go low. It will reset or clear the output Q. So you have clear, and then Q will go low. So this is latches, and there are a couple of points which are mentioned here, so I'm going to quickly read them. So a fundamental digital storage device is called your latch, and the act of storing data for a time such as to latch. So all the flip-flops which we saw previously, they are also called latches, a latch. And that's what is mentioned here. The RS flip-flop is an example of a latch. D flip-flop is an example of latch. JK flip-flop is also an example of latch. And then they are available in different IC forms in 4-bit, 8-bit, 9-bit, 10-bit, etc. And they are commonly embedded in complex ICs. So these are some quick points to remember about the latches. Now let's go to the next slide. So there are a couple of questions here. A fundamental digital storage device is sometimes called your latch. The job of a latch can be performed by a gate or a D flip-flop. So it will be performed by the D flip-flop. So D flip-flop is the answer. And then we say that to latch is the act of storing the data for a time. Is it true or false? Yes, it is true. So answer is true. And then latches are commonly embedded in more complex ICs and serve as temporary memory devices. So is it true or false? This is true. Now next we are going to see the application of latched encoder and decoder system. So you see we have a keypad here from where we can give the decimal input, and then we have an encoder here. And then we have a NOT gate here which will convert the inverted BCD into the BCD. And then we have a latch decoder, and which will decode the input and send it to the display. And here we have a decimal display. And then we have a latch enable circuit over here, you can see, which is connected from the output of the keypad to the input of the decoder. And then we have a clock pulse which is going from here to the decoder and then to the decimal display. Okay, so let's see this type of circuit you have made in your lab experiment also, or you will be making. And so let's see how it works. So you send the input through this keypad, you insert some decimal from 1 to 10, which is active low input, which is active low keypad switches. And then what will happen, your output from decimal 0 through 9 can be displayed on the LCD screen here based on what you sent here. And then you have an encoder here, which is the IC, and it encodes one of 10 active low inputs to 4-bit inverted BCD. Okay, so that's what you see here, inverted BCD, and that's why you have a NOT gate to get the your BCD here. And then you have a decoder, and decoder basically decode the BCD into the 7-segment display code, and then driving out of phase signals active LCD segments, and then latch inputs, signal latches inputs and displays. And then you have a clock here, and clock basically is your continuous clock signal is sent from here both to the decoder and to the IC LCD display screen. So yes, so this clock is going to the decoder and your display screen. And then you have latch enable, which is basically logic gate, generates the positive latch enable pulse whenever your input key is pressed. Okay, so it will generate your positive latch enable pulse every time you press the input, any decimal input to the keypad. Now next we have this complement NOT gate, which will basically inverts your inverted BCD into 4-bit BCD. So this latch decoder encoder system can be become a DIY hardware project in the lab. So you can actually make a PCB board and you can put all these components and see how it works. Now next we have triggering of flip-flops. So there are basically two types of triggering, level triggering, and then you have the edge triggering. So in the level triggering, your data is transferred from input to output of a flip-flop anytime the clock pulse is high. That is called your level triggering. So I'll show you here in this timing in this clock where are the level trigger. And then you have another one is the edge triggering. So you saw in the flip-flop we use the edge triggering, which is basically used to transfer the data from input to output of a flip-flop on the rising edge. If you have the rising edge, then it goes from low to high, and if you have the falling edge, then it goes from high to low. So low to high and high to low of the clock pulse. And edge triggering may be either positive edge triggered or negative edge triggered. Master slave triggering is an older technique using the whole clock pulse, but think of a master slave flip-flop as having a negative edge triggering. So let's see how it works here. So this is your level triggering, which we talked about here first. This is called your level triggering. So this is your positive edge triggering right now you see here, and this is your negative edge triggering which you see here. So this was your level, this is your positive edge triggering and negative edge triggering. In positive it goes from low to high, and in negative it goes from high to low. So these are the mainly two types of triggering we use. In first we have level, and then in the edge triggering we have two, positive and negative triggering, which are used in your flip-flop. Now let's see next. So next is the quiz. If a flip-flop triggers on the low to high transition of the clock pulse, low to high, so what type of triggering it is? Its answer is already there, so it is a positive edge triggering. And then you have CB. So at B, what type of triggering is this? This is a negative triggering. So negative triggering, and then you have, sorry, negative edge triggering, and this was positive edge triggering. And then you have C here. When you trigger here, then this is called your level triggering. So that's why you have level here. Now next we have Schmitt trigger operation. So let's see. We have input going in here, and then output is this, a square waveform. So this is a Schmitt trigger, and it's an example of a Schmitt trigger inverter, which is being used to square up the input signal and make it more useful. So this Schmitt trigger you see here is basically reshaping the waveform. Okay, so you have sine wave going in here, and it is making it a square wave. So this is basically called your signal conditioning, and Schmitt triggers, they are widely used in signal conditioning and are these are widely used in that, and they have fast rise and fall times, almost like instantaneous. You can see here as it goes, and your square wave basically comes out at the output side. So this is Schmitt trigger device. It basically squares up the input. Now let's see some quiz questions. The symbol at the lower right is that of a Schmitt trigger. So this is the answer. The input signal to the Schmitt trigger inverter is a sine wave, and the output will be square wave. So I square wave is the answer. And then a Schmitt trigger device will digitize or square up input signals with slow rise times and slow fall times. Is it true or false? Yes, it is true. That is what we saw in the previous slide. Now this is the review of the lecture. So we learned about combinational versus sequential logic circuits. We learned about RS flip-flops. We also learned about, so in this we learned about NOR and NAND RS flip-flop. And then we learned about clocked RS flip-flop, D flip-flop, JK flip-flop, latches. We saw application of latch encoder decoder, triggering of flip-flops we saw, and then we saw Schmitt trigger devices. So this is the end of the lecture. Thank you so much for watching.